Today, we're going to jump into section 8.4, which is slightly different than the first three sections of chapter 8. We're going to start studying what we call trig identities. First, what we're going to do is work on just exposing you to the different trig identities that exist. And then you'll start verifying, proving that the certain identities are true. So for now, what we're going to do is just get you comfortable looking at the different identities. It might seem overwhelming, but it's not as challenging as you think if you kind of work through the assignments and use the appropriate identities. So these are just tools that you're going to need to recognize and use to get through some of the problems. So the first things we're going to start with are what we call the reciprocal identities, which you've been familiar with. We're just going to view them from a different perspective. So sine theta and cosecant theta, these are reciprocal identities or reciprocal functions, right? So sine of an angle is equal to the y over r ratio, and then the cosecant of the same angle is equal to the r over the y. Given that, then what we can do is we can turn around and say that the sine of an angle is equal to 1 divided by the cosecant of the same angle. And then this can translate over here to the left as the same relationship. The cosecant of an angle is equal to 1 over sine of an angle. Then the same applies for cosine of an angle is equal to 1 over secant of an angle, which also means that the secant of an angle is equal to 1 over the cosine of an angle. Again, these are reciprocals. Tangent of an angle is equal to 1 over cotangent of an angle. And cotangent of an angle is equal to 1 over tangent of an angle. So just to clarify, when I'm saying angle here, we're talking about the same angle measurement each time. So your idea here is like you're going to need to, as you're working through some of these problems, sometimes you'll have to take cosecant and convert it to 1 over sine, or vice versa. Sometimes you'll see 1 over sine and need to convert it to cosecant. Or we'll see sine theta and we need to convert it to 1 over cosecant. So we're going to be, it's almost like a puzzle we're getting into here. So these are the first three, what we call reciprocal identities. And I'll also point out down here that these identities are actually proportions, right? So it's a one-term expression equal to a one-term expression. And when you have a proportion like that, we can manipulate it a little. Meaning if I needed to, I could square both sides of this, or any of these proportion type identities. So the cosecant identity up here, maybe the problem I'm working on isn't necessarily 1 over sine theta. Maybe it's 1 over sine squared theta. Well, we can add exponents of 2 and even 3 sometimes to work with these. So cosecant squared of an angle is equal to 1 over sine squared of the same angle, which also means sine squared of an angle is equal to 1 over cosecant squared of an angle. And the same with the other 4 identities. We can add these exponents or remove the exponents if necessary to produce manipulated identities, right? So, but what your priority is, you could memorize all 6. I actually like to memorize these 3 in blue, and then just know since they're reciprocals, I can convert them in this direction as well. Next up are what we call the quotient identities. You've had some exposure to this already. So, if we remember, tangent of an angle is equal to the y over the x. Well, if sine of an angle is equal to the y and cosine of an angle is equal to the x, then tangent of an angle is equal to sine of the same angle divided by cosine of the same angle. And since tangent and cotangent are reciprocal identities, then we could also express it this way. Remember, cotangent is the x divided by the y, so then we can replace cotangent with cosine of an angle divided by sine of that angle. Or if we had cosine theta over sine theta, we could replace it with cotangent theta. And again, these two are proportions. So because they're proportions, we could add exponents to both sides of these identities, and they remain, the integrity of the identity remains. Now I want to point out something about these exponents right here. So in trig, we add the exponent after the tangent function before the angle. And that's to prevent readers from being a little bit confused. So these expressions here with these exponents, this is really what it is. You would take the sine of the angle and then you would square that value. We express it this way instead of writing it as grouping signs here. And this is pretty much to prevent people from thinking that the exponent squared is not actually on the angle itself. That can be misleading. So we're not squaring the angle, we're squaring the sine of the angle, right? So this is one of the reasons why we don't put the exponent outside here, because often students will, or readers will think that we're squaring the angle. That is not true, right? So we're actually squaring the trig function, but this is the notation we use, and this is the notation you're going to need to use. Next up are what we call even and odd functions. You won't use these as much, but you will use them. So we have the sine and the tangent, even odd identities. The sine and the tangent are similar. These are considered what we call odd functions. And basically what that means is if I have the sine of some negative angle, well, that's going to be equivalent to -1 times the sine of the positive version of that angle. Here's an example. Sine of -5 pi over 6 is the same value as -1 times sine of 5 pi over 6. Point out here that we're not factoring a negative out of the angle. That's not what's happening. We're just, the identity is that this value is the opposite, -1 here, of sine of the positive version of that angle. Tangent is the same way, right? So the tangent of a negative angle contains the same value as -1 times tangent of that positive angle, and you can see that here. Cosine's a little different. Cosine is considered an even function, so cosine of a negative angle is equal to cosine of the positive angle, right? They have the same value regardless whether the angle is negative or positive, as long as the angles are opposite. So cosine of -pi over 3 is equal to cosine of positive pi over 3 here. So these are considered even and odd, and just a quick summary of why. This is a standard sine function. So if I look at sine of -90 degrees, that is equivalent to -1. If I look at sine of positive 90 degrees, that is equivalent to +1. So in this particular case, sine of -90 equals -1. Over here, sine of positive 90 equals 1, but the identity says it's going to be the opposite of that. So we multiply it by -1 there, and you can kind of see that here, right? This is what we call rotational symmetry, but for every positive angle here, there's another negative angle over here that has an opposite output value, and that's how the odd identity works. So that works the same for sine and tangent. Cosine, on the other hand, there's symmetry on the cosine curve about the y-axis here. So the cosine of -180 is down here at -1 on the graph. And if I took the cosine of positive 180, it's also equal to -1 down here on the graph. So the cosine function produces the same value regardless of the angle, as long as they're opposite angles themselves. So these are considered even and odd identities. And then the next big one here, you're going to use this often, is considered the Pythagorean identity. Pythagorean, you should think Pythagorean theorem. That's why we're using this term. So here I have a unit circle, and I'm going to just explain how it works, right? So the radius of the circle is 1. I have an angle in the circle right here. The hypotenuse of this, or the radius of the circle is 1. So this angle length right here, this ray, is 1 unit long. And if we view it as a right triangle where the 90 degrees on the x-axis, we can kind of make sense of this Pythagorean identity. So just triangle speaking, right triangle speaking, we define the small side of this triangle oriented on the x-axis as x. The long leg of the triangle, vertical leg, we express it as y, right? So this green point right here is the point xy. And we know that the radius of the circle, or the hypotenuse of this triangle, is equal to 1. So that can be expressed with the Pythagorean theorem. X squared plus y squared equals 1 squared right here. And we've been working with that just not as formal as we're going to do now. We also know that if we speak in terms of the angle here, we know that the cosine of this angle theta right here is equal to this leg right here, this that we defined as x. So then we can actually say that this length, this small leg horizontal right here, we could also call cosine theta, which is something we've been working on, but we're just viewing it from a different perspective now. Same with the y. So the sine of this angle is equivalent to the vertical leg here. So we can express this side as sine theta instead of y. And radius or hypotenuse stays the same as 1. So then this is what's going to allow us to justify this Pythagorean identity here, which is cosine squared theta plus sine squared theta equals 1. This is a big identity, and you're going to use it often. And, unfortunately, you're going to have to memorize some of these.